Hello, 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 and welcome to section number 4 of the Learn PyTorch for Deep Learning course. We have custom datasets with PyTorch. Now, before we dive into what we're going to cover, let's answer the most important question: where can you get help? Now, we've been through this a few times now, but it's important to reiterate. Follow along with the code as best you can. We're going to be writing a bunch of PyTorch code. Remember the motto: if in doubt, run the code. That's in line with try it for yourself. If you'd like to reach or read the doc string, you can press Shift Command plus space in Google Colab. Or if you're on Windows, Command might be Control. Then if you're still stuck, you can search for it. Two of the resources you'll probably come across is Stack Overflow or the wonderful PyTorch documentation, which we've had a lot of experience with so far. Then, of course, try again, go back through your code. If in doubt, code it out, or if in doubt, run the code. And then finally, if you're still stuck, ask a question on the PyTorch Deep Learning Discussions GitHub page. So if I click this link, we come to Mr. D. Burke / PyTorch Deep Learning. The URL is here. We've seen this before. If you have a trouble or a problem with any of the course, you can start a discussion and you can select a category: general, ideas, polls, Q&A, and then we can go here. Video, put the video number in, so 99 for example. My code doesn't do what I'd like it to. So say your problem, and then come in here, write some code here, and then my question is something, something, something. Click start discussion, and then we can help out. And then if we come back to the discussions, of course, you can search for what's going on. So if you have an error and you feel like someone else might have seen this error, you can, of course, search it and find out what's happening. Now, I just want to highlight again, the resources for this course are at learnpytorch.io. We are up to section 4. This is a beautiful online book version of all the materials we are going to cover in this section. So spoiler alert, you can use this as a reference. And then, of course, in the GitHub, we have the same notebook here, PyTorch Custom Datasets. This is the ground truth notebook. So check that out if you get stuck. So I'm just going to exit out of this. We've got PyTorch Custom Datasets at learnpytorch.io. And then, of course, the discussions tab for the Q&A. Now, if we jump back to the keynote, what do we have? We might be asking, what is a custom dataset? Now, we've built a fair few PyTorch deep learning neural networks so far on various datasets such as Fashion MNIST. But you might be wondering, hey, I've got my own dataset, or I'm working on my own problem. Can I build a model with PyTorch to predict on that dataset? And the answer is yes. However, you do have to go through a few pre-processing steps to make that dataset compatible with PyTorch. And that's what we're going to be covering in this section. And so, I'd like to highlight the PyTorch domain libraries. Now, we've had a little bit of experience before with Torch Vision, such as if we wanted to classify whether a photo was of pizza, steak, or sushi. So a computer vision image classification problem. Now, there's also text, such as if these reviews are positive or negative, and you can use Torch text for that. But again, these are only just one problem within the vision space, within the text space. I want you to just understand that if you have any type of vision data, you probably want to look into Torch Vision. And if you have any kind of text data, you probably want to look into Torch Text. And then if you have audio, such as if you wanted to classify what song was playing, this is what Shazam does. It uses the input sound of some sort of music and then runs a neural network over it to classify it to a certain song. You can look into Torch Audio for that. And then if you'd like to recommend something, such as you ever have an online store, or if you're Netflix or something like that, and you'd like to have a homepage that updates for recommendations, you'd like to look into Torch Rec, which stands for Recommendation System. And so this is just something to keep in mind, because each of these domain libraries has a datasets module that helps you work with different datasets from different domains. And so different domain libraries contain data loading functions for different data sources. So Torch Vision, let's just go into the next slide. We have problem space, vision. For pre-built datasets, so existing datasets like we've seen with Fashion MNIST, as well as functions to load your own vision datasets, you'll want to look into torchvision.datasets. So if we click on this, we have built-in datasets. This is the PyTorch documentation. And if we go here, we have Torch Audio, Torch Text, Torch Vision, Torch Rec, Torch Data. Now, at the time of recording, which is April 2022, Torch Data is currently in beta, but it's going to be updated over time. So just keep this in mind, updated over time to add even more ways to load different data resources. But for now, we're just going to get familiar with Torch Vision datasets. If we went into Torch Text, there's another Torch Text.datasets. And then if we went into Torch Audio, we have Torch Audio.datasets. And so you're noticing a trend here that depending on the domain you're working in, whether it be vision, text, audio, or your data is recommendation data, you'll probably want to look into its custom library within PyTorch. And of course, the bonus is Torch Data. It contains many different helper functions for loading data and is currently in beta as of April 2022. So that by the time you watch this, Torch Data may be out of beta. And then that should be something that's extra curriculum on top of what we're going to cover in this section. So let's keep going. So this is what we're going to work towards building. Food Vision Mini. So we're going to load some data, namely some images of pizza, sushi, and steak from the Food 101 dataset. We're going to build an image classification model, such as the model that might power a food vision recognition app or a food image recognition app. And then we're going to see if it can classify an image of pizza as pizza, an image of sushi as sushi, and an image of steak as steak. So this is what we're going to focus on. We want to load, say we had images existing already of pizza, sushi, and steak. We want to write some code to load these images of food, so our own custom data set for building this Food Vision Mini model, which is quite similar to if you go to, this is the project I'm working on personally, Nutrify.app. This is a food image recognition model. Here we go. So it's still a work in progress as I'm going through it, but you can upload an image of food and Nutrify will try to classify what type of food it is. So do we have steak? There we go. Let's upload that. Beautiful. Steak. So we're going to be building a similar model to what powers Nutrify. And then there's the macronutrients for the steak, yada, yada, yada. If you'd like to find out how it works, I've got all the links here, but that's at Nutrify.app. So let's keep pushing forward. We'll go back to the keynote. This is what we're working towards. As I said, we want to load these images into PyTorch so that we can build a model. We've already built a computer vision model. So we want to figure out how do we get our own data into that computer vision model. And so, of course, we'll be adhering to our PyTorch workflow that we've used a few times now. So we're going to learn how to load a data set with our own custom data rather than an existing data set within PyTorch. We'll see how we can build a model to fit our own custom data set. We'll go through all the steps that's involved in training a model, such as picking a loss function and an optimizer. We'll build a training loop. We'll evaluate our model. We'll improve through experimentation. And then we can see save and reloading our model, but we're also going to practice predicting on our own custom data, which is a very, very important step whenever training your own models. So what we're going to cover broadly, we're going to get a custom data set with PyTorch, as we've said. We're going to become one with the data. In other words, preparing and visualizing it. We'll learn how to transform data for use with a model, very important step. We'll see how we can load custom data with pre-built functions and our own custom functions. We'll build a computer vision model, aka Food Vision Mini, to classify pizza, steak, and sushi images, so a multi-class classification model. We'll compare models with and without data augmentation. We haven't covered that yet, but we will later on. And finally, we'll see how we can, as I said, make predictions on custom data. So this means data that's not within our training or our test data set. And how are we going to do it? Well, we could do it cooks or chemists, but I like to treat machine learning as a little bit of an art, so we're going to be cooking up lots of code. With that being said, I'll see you in Google Colab. Let's code. Welcome back to the PyTorch cooking show. Let's now learn how we can cook up some custom data sets. I'm going to jump into Google Colab, so colab.research.google.com. And I'm going to click New Notebook. Just going to make sure this is zoomed in enough for the video. Wonderful. So I'm going to rename this notebook 04, because we're up to section 04. And I'm going to call it PyTorch Custom Datasets _ video, because this is going to be one of the video notebooks, which has all the code that I write during the videos, which is of course contained within the video notebooks folder on the PyTorch Deep Learning repo. So if you'd like the resource or the ground truth notebook for this, I'm going to just put a heading here, 04 PyTorch Custom Datasets video notebook. Make that bigger. And then we'll put resources. So book version of the course materials for 04. We'll go there. And then we'll go ground truth version of notebook 04, which will be the reference notebook that we're going to use for this section. Come into PyTorch custom datasets, and then we can put that in there. Wonderful. So the whole synopsis of this custom dataset section is we've used some datasets with PyTorch before, but how do you get your own data into PyTorch? Because that's what you want to start working on, right? You want to start working on problems of your own. You want to come into any sort of data that you've never worked with before, and you want to figure out how do you get that into PyTorch. So one of the ways to do so is via custom datasets. And then I want to put a note down here. So we're going to go 0, section 0 is going to be importing PyTorch and setting up device agnostic code. But I want to just stress here that domain libraries. So just to reiterate what we went through last video, so depending on what you're working on, whether it be vision, text, audio, recommendation, something like that, you'll want to look into each of the PyTorch domain libraries for existing data loader or data loading functions and customizable data loading functions. So just keep that in mind. We've seen some of them. So if we go Torch Vision, which is what we're going to be looking at, Torch Vision, we've got data sets and we've got documentation. We've got data sets for each of the other domain libraries here as well. So if you're working on a text problem, it's going to be a similar set of steps to what we're going to do with our vision problem when we build Food Vision Mini. What we have is a data set that exists somewhere, and what we want to do is bring that into PyTorch so we can build a model with it. So let's import the libraries that we need. So we're going to import Torch, and we'll probably import NN. So we'll import that from PyTorch, and I'm just going to check the Torch version here. So note, we need PyTorch 1.10.0 plus is required for this course. So if you're using Google Colab at a later date, you may have a later version of PyTorch. I'm just going to show you what version I'm using. Just going to let this load. We're going to get this ready. We're going to also set up device agnostic code right from the start this time, because this is best practice with PyTorch. So this way, if we have a CUDA device available, our model is going to use that CUDA device, and our data is going to be on that CUDA device. So there we go, wonderful. We've got PyTorch 1.10.0 plus CUDA 1.1.1, maybe that's 11.1. So let's check if CUDA dot is available. Now, I'm using Google Colab. We haven't set up a GPU yet, so it probably won't be available yet. Let's have a look. Wonderful. So because we've started a new Colab instance, it's going to use the CPU by default. So how do we change that? We come up to runtime, change runtime type. I'm going to go hardware accelerator, GPU. We've done this a few times now. I am paying for Google Colab Pro. So one of the benefits of that is that Google Colab reserves faster GPUs for you. You do not need Google Colab Pro, as I've said, to complete this course. You can use the free version, but just recall Google Colab Pro tends to give you a better GPU just because GPUs aren't free. Wonderful. So now we've got access to a GPU. CUDA, what GPU do I have? NVIDIA SMI, I have a Tesla P100 with 16 gigabytes of memory, which will be more than enough for the problem that we're going to work on in this video. So, I believe that's enough to cover for the first coding video. In the next section, we are working with custom datasets after all. In the next video, let's get some data, hey? Now, as I said in the last video, we can't cover custom datasets without some data. So let's get some data and just remind ourselves what we're going to build, and that is Food Vision Mini. So we need a way of getting some food images. And if we go back to Google Chrome, Torch Vision Datasets has plenty of built-in datasets, and one of them is the Food 101 dataset. Food 101. So if we go into here, this is going to take us to the original Food 101 website. So Food 101 is 101 different classes of food. It has a challenging data set of 101 different food categories with 101,000 images. So that's quite a beefy data set. And so for each class, 250 manually reviewed test images are provided. So we have per class, 101 classes, 250 testing images, and we have 750 training images. Now, we could start working on this entire data set straight from the get-go, but to practice, I've created a smaller subset of this data set, and I'd encourage you to do the same with your own problems. Start small and upgrade when necessary. So I've reduced the number of categories to 3 and the number of images to 10%. Now, you could reduce this to an arbitrary amount, but I've just decided 3 is enough to begin with and 10% of the data. And then if it works, hey, you could upscale that on your own accord. And so I just want to show you the notebook that I used to create this data set, and as extra curriculum, you could go through this notebook. So if we go into extras, 04 custom data creation, this is just how I created the subset of data. So making a data set to use with notebook number 4, I created it in custom image data set or image classification style. So we have a top level folder of pizza, steak, and sushi. We have a training directory with pizza, steak, and sushi images. And we have a test directory with pizza, steak, and sushi images as well. So you can go through that to check it out, how it was made. But now, and also, if you go to learnpytorch.io, section 4, there's more information here about what Food 101 is. So get data, here we go. There's all the information about Food 101. There's some resources, the original Food 101 dataset, Torch Vision datasets, Food 101, how I created this dataset, and actually downloading the data. But now we're going to write some code because this dataset, the smaller version that I've created, is on the PyTorch deep learning repo under data, and then we have pizza, steak, sushi.zip. Oh, this one is a little spoiler for one of the exercises for this section, but you'll see that later. So let's go in here. Let's now write some code to get this data set from GitHub, pizza, steak, sushi.zip, and then we'll explore it. We'll become one with the data. So I just want to write down here, our data set is a subset of the Food 101 data set. Food 101 starts with 101 different classes of food. So we could definitely build computer vision models for 101 classes, but we're going to start smaller. Our data set starts with 3 classes of food and only 10% of the images. So let's write here, and 1,000 images per class, which is 750 training, 250 testing, and we have about 75 training images per class and about 25 testing images per class. So why do this? When starting out ML projects, it's important to try things on a small scale and then increase the scale when necessary. The whole point is to speed up how fast you can experiment. Because there's no point trying to experiment on things that if we try to train on 100,000 images to begin with, our models might take half an hour to train at a time. So at the beginning, we want to increase the rate that we experiment at. And so let's get some data. We're going to import requests so that we can request something from GitHub to download this URL here. Then we're also going to import zip file from Python because our data is in the form of a zip file right now. Then we're going to get pathlib because I like to use paths whenever I'm dealing with file paths or directory paths. So now let's set up a path to a data folder. And this, of course, will depend on where your data set lives, what you'd like to do, but I typically like to create a folder over here called data. And that's just going to store all of my data for whatever project I'm working on. So data path equals path data. And then we're going to go image path equals data path slash pizza steak sushi. We're going to have images from those three classes. Pizza, steak, and sushi are 3 of the classes out of the 101 in Food 101. So if the image folder doesn't exist, so if our data folder already exists, we don't want to re-download it. But if it doesn't exist, we want to download it and unzip it. So if image path is dir, so we want to print out the image path directory already exists, skipping download. And then if it doesn't exist, we want to print image path does not exist, creating one. Beautiful. And so we're going to go image path.mkdir to make a directory. We want to make its parents if we need to, so the parent directories, and we want to pass exist OK equals true so we don't get any errors if it already exists. And so then we can write some code. I just want to show you what this does if we run it. So our target directory data slash pizza steak sushi does not exist. It's creating one. So then we have now data and inside pizza steak sushi. Wonderful. But we're going to fill this up with some images so that we have some data to work with. And then the whole premise of this entire section will be loading this data of just images into PyTorch so that we can build a computer vision model on it. But I just want to stress that this step will be very similar no matter what data you're working with. You'll have some folder over here, or maybe it'll live on the cloud somewhere. Who knows, wherever your data is, but you'll want to write code to load it from here into PyTorch. So let's download pizza, steak, and sushi data. So I'm going to use with, I'll just X over here so we have more screen space. With open, I'm going to open the data path slash the file name that I'm trying to open, which will be pizzasteaksushi.zip. And I'm going to write binary as F. So this is essentially saying I'm doing this in advance because I know I'm going to download this folder here. So I know the file name of it, pizzasteaksushi.zip. I'm going to download that into Google Colab and I want to open it up. So request equals request.get. And so when I want to get this file, I can click here. And then if I click download, it's going to, what do you think it's going to do? Well, let's see. If I wanted to download it locally, I could do that. And then I could come over here and then I could click upload if I wanted to. So upload to session storage, I could upload it from that, but I prefer to write code so that I could just run this cell over again and have the file, instead of being downloaded to my local computer, it just goes straight into Google Colab. So to do that, we need the URL from here. And I'm just going to put that in there. It needs to be as a string. Excuse me. I'm getting trigger happy on the shift and enter. Wonderful. So now I've got a request to get the content that's in here. And GitHub can't really show this because this is a zip file of images. Spoiler alert. Now, let's keep going. We're going to print out that we're downloading pizza, steak, and sushi data. ... And then I'm going to write to file the request.content. So the content of the request that I just made to GitHub. So that's request is here, using the Python request library to get the information here from GitHub. This URL could be wherever your file is being stored. And then I'm going to write the content of that request to my target file, which is this here. So if I just copy this, I'm going to write the data to here, data path / pizza steak sushi zip. And then because it's a zip file, I want to unzip it. So unzip pizza steak sushi data. Let's go with zip file. So we imported zip file up there, which is a Python library to help us deal with zip files. I'm going to use zipfile.zip file. I'm going to pass it in the data path. So just the path that we did below. Data path / pizza steak sushi .zip. And this time, instead of giving it write permissions, so that's what WB stands for. It stands for write binary. I'm going to give it read permissions. So I want to read this target file instead of writing it. And I'm going to go as zipref. We could call this anything really, but zipref is kind of, you'll see this a lot in different Python examples. So we're going to print out again. So unzipping pizza, steak, and sushi data. Then we're going to go zip _ref dot extract all, and we're going to go image path. So what this means is it's taking the zip ref here and it's extracting all of the information that's within that zip ref, so within this zip file, to the image path, which is what we created up here. So if we have a look at image path, let's see that. Image path. Wonderful. So that's where all of the contents of that zip file are going to go into this file. So let's see it in action. You ready? Hopefully it works. 3, 2, 1, run. File is not a zip file. Oh no, what did we get wrong? So did I type this wrong? .zip data path. Oh, we got the zip file here. Pizza steak sushi .zip read data path. Okay, I found the error. So this is another thing that you'll have to keep in mind, and I believe we've covered this before, but I like to keep the errors in these videos so that you can see where I get things wrong, because you never write code right the first time. So we have this link in GitHub. We have to make sure that we have the raw link address. So if I come down to here and copy the link address from the download button, you'll notice a slight difference if we come back into here. So I'm just going to copy that there. So if we step through this, GitHub, Mr. Debug, PyTorch Deep Learning, we have raw instead of blob. So that is why we've had an error, is that our code is correct, it's just downloading the wrong data. So let's change this to the raw. So just keep that in mind, you must have raw here. And so let's see if this works. Do we have the correct data? Oh, we might have to delete this. Oh, there we go. Test, beautiful. Train, pizza, steak, sushi, wonderful. So it looks like we've got some data, and if we open this up, what do we have? We have various JPEGs. Okay, so this is our testing data. And if we click on there, we've got an image of pizza. Beautiful. So we're going to explore this a little bit more in the next video, but that is some code that we've written to download datasets or download our own custom dataset. Now, just recall that we are working specifically on a pizza, steak, and sushi problem for computer vision. However, our whole premise is that we have some custom data and we want to convert these. How do we get these into tensors? That's what we want to do. And so the same process will be for your own problems. We'll be loading a target data set and then writing code to convert whatever the format the data set is in into tensors for PyTorch. So I'll see you in the next video. Let's explore the data we've downloaded. Welcome back. In the last video, we wrote some code to download a target dataset, our own custom dataset from the PyTorch Deep Learning data directory. And if you'd like to see how that dataset was made, you can go to PyTorch Deep Learning /extras. And it's going to be in the custom data creation notebook here for 04. So I've got all the code there. All we've done is take data from the Food 101 dataset, which you can download from this website here, or from Torch Vision. So if we go to Torch Vision Food 101, we've got the dataset built into PyTorch there. So I've used that dataset from PyTorch and broken it down from 101 classes to 3 classes so that we can start with a small experiment. So there we go. Get the training data, datasets Food 101, and then I've customized it to be my own style. So if we go back to Colab, we've now got pizza steak sushi, a test folder which will be our testing images, and a train folder which will be our training images. This data is in standard image classification format, but we'll cover that in a second. What we're going to do in this video is kick off section number 2, which is becoming one with the data, which is one of my favorite ways to refer to data preparation and data exploration. So becoming one with the data. And I'd just like to show you one of my favorite quotes from Abraham loss function. So if I had 8 hours to build a machine learning model, I'd spend the first 6 hours preparing my data set. And that's what we're going to do. Abraham loss function sounds like he knows what is going on, but since we've just downloaded some data, let's explore it, hey? And we'll write some code now to walk through each of the directories. How you explore your data will depend on what data you've got. So we've got a fair few different directories here with a fair few different folders within them. So how about we walk through each of these directories and see what's going on? If you have visual data, you probably want to visualize an image. So we're going to do that in a second too. We'll write a little doc string for this helper function. So walks through dir path, returning its contents. Now, just in case you didn't know, Abraham loss function does not exist as far as I know, but I did make up that quote. So we're going to use the os.walk function, os.walk, and we're going to pass it in a dir path. And what does walk do? We can get the doc string here. Directory tree generator. For each directory in the directory tree, rooted at the top, including top itself, but excluding dot and dot dot, yields a 3-tuple, dir path, dir names, and file names. You can step through this in the Python documentation if you'd like, but essentially it's just going to go through our target directory, which in this case will be this one here, and walk through each of these directories, printing out some information about each one. So let's see that in action. This is one of my favorite things to do if we're working with standard image classification format data. So there are length dir names, directories, and let's go len, file names. I say it length, like I've got the G on the end, but it's just len. Images in, let's put in here, dir path. So a little bit confusing if you've never used walk before, but it's so exciting to see all of the information in all of your directories. Oh, we didn't run it. Let's check our function now. Walk through dir, and we're going to pass it in the image path, which is what? Well, it's going to show us. Oh, beautiful. So let's compare what we've got in our printout here. There are 2 directories and 0 images in data pizza steak sushi. So this one here, there's 0 images, but there's 2 directories. Test and train, wonderful. And there are 3 directories in data pizza steak sushi test. Yes, that looks correct. 3 directories, pizza, steak, sushi. And then we have 0 directories and 19 images in pizza, steak, sushi / test steak. If we have a look at this. So that means there's 19 testing images for steak. Let's have a look at one of them. There we go. Now, again, these are from the Food 101 dataset, the original Food 101 dataset, which is just a whole bunch of images of food, 100,000 of them. There's some steak there. Wonderful. And we're trying to build a food vision model to recognize what is in each image. Then if we jump down to here, we have 3 directories in the training directory. So we have pizza, steak, sushi, and then we have 75 steak images, 72 sushi images, and 78 pizza. So slightly different, but very much the same numbers. They're not too far off each other. So we've got about 75 or so training images, and we've got about 25 or so testing images per class. Now, these were just randomly selected from the Food 101 dataset, 10% of 3 different classes. So let's keep pushing forward, and we're going to set up our training and test paths. So I just want to show you, we'll just set up this, and then I'll just show you the standard image classification setup. Image path.train, and we're going to go tester. So if you're working on an image classification problem, we want to set this up as test. And then if we print out the trainer and the tester, this is what we're going to be trying to do. We're going to write some code to go, hey, look at this path for our training images, and look at this path for our testing images. And so this is the standard image classification data format, is that you have your overall dataset folder, and then you have a training folder dedicated to all of the training images that you might have, and then you have a testing folder dedicated to all of the testing images that you might have. And you could have a validation data set here as well if you wanted to. But to label each one of these images, the class name is the folder name. So all of the pizza images live in the pizza directory. The same for steak, and the same for sushi. So depending on your problem, your own data format will depend on whatever you're working on. You might have folders of different text files or folders of different audio files. But the premise remains, we're going to be writing code to get our data here into tensors for use with PyTorch. And so where does this come from, this image data classification format? Well, if we go to the Torch Vision Datasets documentation, as you start to work with more datasets, you'll start to realize that there are standardized ways of storing specific types of data. So if we come down to here, base classes for custom datasets, we'll be working towards using this image folder dataset. But this is a generic data loader where the images are arranged in this way by default. So I've specifically formatted our data to mimic the style that this pre-built data loading function is for. So we've got a root directory here in case of we were classifying dog and cat images. We have root, then we have a dog folder, then we have various images, and the same thing for cat. This would be dog versus cat. But the only difference for us is that we have food images and we have pizza, steak, sushi. If we wanted to use the entire Food 101 dataset, we would have 101 different folders of images here, which is totally possible, but to begin with, we're keeping things small. So let's keep pushing forward. As I said, we are dealing with a computer vision problem. So what's another way to explore our data other than just walking through the directories themselves? Let's visualize an image, hey? But we've done that before with just clicking on the file. How about we write some code to do so? We'll replicate this, but with code. I'll see you in the next video. Welcome back. In the last video, we started to become one with the data. And we learned that we have about 75 images per training class and about 25 images per testing class. And we also learned that the standard image classification data structure is to have the steak images within the steak folder of the training data set, and the same for test, and the pizza images within the pizza folder, and so on for each different image classification class that we might have. So if you want to create your own data set, you might format it in such a way that your training images are living in a directory with their classification name. So if you wanted to classify photos of dogs and cats, you might create a training folder of train/dog, train/cat, put images of dogs in the dog folder, images of cats in the cat folder, and then the same for the testing data set. But the premise remains, I'm going to sound like a broken record here. We want to get our data from these files, whatever files they may be in, whatever data structure they might be in, into tensors. But before we do that, let's keep becoming one with the data, and we're going to visualize an image. So visualizing an image, and you know how much I love randomness. So let's select a random image from all of the files that we have in here, and let's plot it, hey? Because we could just click through them and visualize them, but I like to do things with code. So specifically, let's plan this out. Let's write some code to, number one is get all of the image paths. We'll see how we can do that with the path lib library. We then want to pick a random image path using, we can use Python's random for that. Python's random.choice will pick a single image, random.choice. Then we want to get the image class name. And this is where path lib comes in handy. Class name, recall that whichever target image we pick, the class name will be whichever directory that it's in. So in the case of if we picked a random image from this directory, the class name would be pizza. So we can do that using, I think it's going to be pathlib.path, and then we'll get the parent folder, wherever that image lives. So the parent image, parent folder, the parent directory of our target random image. And we're going to get the stem of that. So we have stem. The stem is the last little bit here. Number 4, what should we do? Well, we want to open the image. So since we're working with images, let's open the image with Python's pill, which is Python image library, which will actually be pillow. So if we go Python pillow, a little bit confusing when I started to learn about Python image manipulation. So pillow is a friendly pill fork, but it's still called pill. So just think of pillow as a way to process images with Python. So pill is the Python imaging library by Frederick Lund. And so Alex Clark and contributors have created pillow. So thank you, everyone. And let's go to number 5. What do we want to do as well? We want to, let's get some metadata about the image. We'll then show the image and print metadata. Wonderful. So let's import random, because machine learning is all about harnessing the power of randomness, and I like to use randomness to explore data as well as model it. So let's set the seed. So we get the same image on both of our ends. So random.seed. I'm going to use 42. You can use whatever you'd like, but if you'd like to get the same image as me, I'd suggest using 42 as well. Now let's get all the image paths. So we can do this because our image path list, we want to get our image path. So recall that our image path is this. So this folder here. I'm just going to close all this. So this is our image path, this folder here. You can also go copy path if you wanted to. We're just going to get something very similar there. That's going to error out. So I'll just comment that. So it doesn't error. That's our path, but we're going to keep it in the POSIX path format. And we can go list. Let's create a list of image path.glob, which stands for grab. I don't actually know what glob stands for, but to me, it's like glob together all of the images that, or all of the files that suit a certain pattern. So glob together for me means stick them all together. And you might be able to correct me if I've got the wrong meaning there. I'd appreciate that. And so we're going to pass in a certain combination. So we want star/star, and then we want star.jpg. Now, why are we doing this? Well, because we want every image path. So star is going to be this first directory here. So any combination, it can be train or test. And then this star means anything for what's inside test. So let's say this first star is equal to test. This second star is equal to anything here. So it could be any of pizza, steak, or sushi. And then finally this star, let's say it was test, pizza. This star is anything in here that is before .jpg. So it could be any one of these files here. Now, this will make more sense once we print it out. So image path list, let's have a look. There we go. So now we've got a list of every single image that's within pizza, steak, sushi. And this is just another way that I like to visualize data, is to just get all of the paths and then randomly visualize it, whether it be an image or text or audio. You might want to randomly listen to it. Recall that each of the domain libraries have different input and output methods for different data sets. So if we come to Torch Vision, we have utils. So we have different ways to draw on images, reading and writing images and videos. So we could load an image via read image, we could decode it, we could do a whole bunch of things. I'll let you explore that as extra curriculum. But now let's select a random image from here and plot it. So we'll go number 2, which was our step up here. Pick a random image. So pick a random image path. Let's get rid of this. And so we can go random image path equals random.choice. Harness the power of randomness to explore our data. Let's get a random image from image path list, and then we'll print out random image path. Which one was our lucky image that we selected? Beautiful. So we have a test pizza image is our lucky random image. And because we've got a random seed, it's going to be the same one each time. Yes, it is. And if we comment out the random seed, we'll get a different one each time. We've got a steak image. We've got another steak image. Another steak image. Oh, 3 in a row. 4 in a row. Pizza. Okay, let's keep going. So we'll get the image class from the path name. So the image class is the name of the directory, because our image data is in standard image classification format, where the image is stored. So let's do that. Image class equals random image path dot parent dot stem, and then we're going to print image class. What do we get? So we've got pizza. Wonderful. So the parent is this folder here, and then the stem is the end of that folder, which is pizza. Beautiful. Well, now what are we up to now? We're working with images. Let's open up the image. So we can open up the image using pill. We could also open up the image with PyTorch here, so with read image, but we're going to use pill to keep things a little bit generic for now. So open image, image equals image. So from pill import image, and the image class has an open function, and we're just going to pass it in here, the random image path. Note, if this is corrupt, if your image is corrupt, this may error. So then you could potentially use this to clean up your data set. I've imported a lot of images with image.open of our target data set here. I don't believe any of them are corrupt, but if they are, please let me know. And we'll find out later on when our model tries to train on it. So let's print some metadata. So when we open our image, we get some information from it. So let's go, our random image path is what? Random image path. We're already printing this out, but we'll do it again anyway. And then we're going to go, the image class is equal to what? Will be the image class. Wonderful. And then we can print out, we can get some metadata about our images. So the image height is going to be img.height. We get that metadata from using the pill library. And then we're going to print out image width, and we'll get img.width. And then we'll print the image itself. Wonderful. And we can get rid of this, and we can get rid of this. Let's now have a look at some random images from our data set. Lovely, we've got an image of pizza there. Now, I will warn you that one of the downsides of working with food data is it does make you a little bit hungry. So there we've got some sushi, and then we've got some more sushi, some steak, and we have a steak. We'll go one more for good luck. And we finish off with some sushi. Oh, that could be a little bit confusing to me. I thought that might be steak to begin with. And this is, do you see now? We'll do one more. Why it's important to sort of visualize your images randomly, because you never know what you're going to come across. And this way, once we visualize enough images, you could do this 100 more times. You could do this 20 more times until you feel comfortable to go, hey, I feel like I know enough about the data now. Let's see how well our model goes on this sort of data. So we'll finish off on this steak image. And now I'll set you a little challenge before the next video, is to visualize an image like we've done here, but this time do it with matplotlib. So try to visualize an image with matplotlib. That's your little challenge before the next video, so give that a go. We want to do a random image as well, so quite a similar setup to this, but instead of printing out things like this, we want to visualize it using matplotlib. So try that out and we'll do it together in the next video. Oh, we are well on the way to creating our own PyTorch custom dataset. We've started to become one with the data. But now, let's continue to visualize another image. I set you the challenge in the last video to try and replicate what we've done here with the pill library with matplotlib. So now, let's give it a go, hey? And why use matplotlib? Well, because matplotlib, and I'm going to import numpy as well, because we're going to have to convert this image into an array. That was a little trick that I didn't quite elaborate on, but I hope you tried to decode it out and figured it out from the errors you received. But matplotlib is one of the most fundamental data science libraries, so you're going to see it everywhere. So it's just important to be aware of how to plot images and data with matplotlib. So turn the image into an array. So we can go image as array, and I'm going to use the numpy method, np as array. We're going to pass it in the image. Recall that the image is the same image that we've just set up here, and we've already opened it with pill. And then I'm going to plot the image. So plot the image with matplotlib, plt.figure, and then we can go fig size equals 10, 7, and then we're going to go plt.imshow, image as array, pass it in the array of numbers. I'm going to set the title here as an f string, and then I'm going to pass in image class equals image class, and then I'm going to pass in image shape, so we can get the shape here. Now this is another important thing to be aware of your different data sets when you're exploring them, is what is the shape of your data, because what's one of the main errors in machine learning and deep learning? It's shape mismatch issues. So if we know the shape of our data, well, we can start to go, okay, I kind of understand what shape I need my model layers to be in, what shape I need my other data to be in. And I'm going to turn the axes off here. Beautiful. So look at what we've got. Now I've just thrown this in here without really explaining it, but we've seen this before in the computer vision section. Is our image shape is 512, 306, 3. Now the dimensions here are height is 512 pixels, the width is 306 pixels, and it has 3 color channels. So what format is this? This is color channels last, which is the default for the pill library. And there's also the default for matplotlib, but PyTorch, recall, is default if we put the color channels at the start, color channels first. Now, there is a lot of debate, as I've said, over which is the best order. It looks like it's leading towards going towards this, but for now, PyTorch defaults to color channels first. But that's okay, because we can manipulate these dimensions to what we need for whatever code that we're writing. And the 3 color channels is what? Red, green, and blue. So if you combine red, green, and blue in some way, shape, or form, you get the different colors here that represent our image. And so if we have a look at our image as array, our image is in numerical format. Wonderful. So, okay, we've got one way to do this for one image. I think we start moving towards scaling this up to do it for every image in our data folder. So let's just finish off this video by visualizing one more image. What do we get? Same premise, the image is now as an array, different numerical values. We've got a delicious looking pizza here of shape 512, 512 with color channels last, and we've got the same thing up here. So that is one way to become one with the data, is to visualize different images, especially random images. You could do the same thing visualizing different text samples that you're working with, or listening to different audio samples. It depends what domain you're working in. So now in the next video, let's start working towards turning all of the images in here, now that we've visualized some of them and become one with the data, we've seen that the shapes are varying in terms of height and width, but they all look like they have 3 color channels because we have color images. But now we want to write code to turn all of these images into PyTorch tensors. So let's start moving towards that. I'll see you in the next video. Hello, and welcome back. In the last video, we converted an image to a NumPy array, and we saw how an image can be represented as an array. But what if we'd like to get this image from our custom dataset over here, pizza steak sushi, into PyTorch? Well, let's cover that in this video. So I'm going to create a new heading here, and it's going to be transforming data. And so what we'd like to do here is, I've been hinting at it the fact the whole time, is we want to get our data into tensor format because that is the data type that PyTorch accepts. So let's write down here, before we can use our image data with PyTorch, now this goes for images, other vision data, it goes for text, it goes for audio, basically whatever kind of data set you're working with, you need some way to turn it into tensors. So that's step number 1, turn your target data into tensors. In our case, it's going to be a numerical representation of our images. And number 2 is turn it into a torch.utils.data.dataset. So recall from a previous video that we've used the dataset to house all of our data in tensor format. And then subsequently, we've turned our datasets, our PyTorch datasets, into torch.utils.data.DataLoader. And a DataLoader creates an iterable or a batched version of our dataset. So for short, we're going to call these dataset and DataLoader. Now, as I discussed previously, if we go to the PyTorch documentation, Torch Vision, for Torch Vision, and this is going to be quite similar for Torch Audio, Torch Text, Torch Rec, Torch Data eventually when it comes out of beta. There are different ways to create such data sets. So we can go into the Datasets module, and then we can find built-in data sets, and then also base classes for custom data sets. But if we go into here, image folder, there's another parameter I'd like to show you, and this is going to be universal across many of your different data types, is the transform parameter. Now, the transform parameter is a parameter we can use to pass in some transforms on our data. So when we load our data sets from an image folder, it performs a transform on those data samples that we've sent in here as the target data folder. Now, this is a lot more easier to understand through illustration rather than just talking about it. So let's create a transform. And the main transform we're going to be doing is transforming our data, and we're turning it into tensors. So let's see what that looks like. So I'm just going to re-import all of the main libraries that we're going to use. So from torch utils.data, let's import DataLoader. And we're going to import from Torch Vision. I'm going to import datasets, and I'm also going to import transforms. Beautiful. And I'm going to create another little heading here. This is going to be 3.1, transforming data with torchvision.transform. So the main transform we're looking to here is turning our images from JPEGs. If we go into train and then we go into any folder, we've got JPEG images. And we want to turn these into tensor representations. So there's some pizza there. If we get out of this, let's see what we can do. How about we create a transform here, write a transform for image, and let's start off by calling it data transform. And I'm going to show you how we can combine a few transforms together. If you want to combine transforms together, you can use transforms.compose. You can also use nn.sequential to combine transforms. but we're going to stick with transforms.compose for now. And it takes a list. And so let's just write out 3 transforms to begin with, and then we can talk about them after we do so. So we want to resize our images to 64, 64. Now, why might we do this? Well, do you recall in the last section, computer vision, we used the tiny VGG architecture? And what size were the images that the tiny VGG architecture took? Well, we replicated the CNN website version, or the CNN Explainer website version, and they took images of size 64, 64. So perhaps we want to leverage that computer vision model later on. So we're going to resize our images to 64, 64. And then we're going to create another transform. And so this is, I just want to highlight how transforms can help you manipulate your data in a certain way. So if we wanted to flip the images, which is a form of data augmentation, in other words, artificially increasing the diversity of our data set, we can flip the images randomly on the horizontal. So transforms.random horizontal flip, and I'm going to put a probability in here of p equals 0.5. So that means 50% of the time, if an image goes through this transform pipeline, it will get flipped on the horizontal axis. As I said, this makes a lot more sense when we visualize it, so we're going to do that very shortly. And finally, we're going to turn the image into a torch tensor. So we can do this with transforms.toTensor. And now, where might you find such transforms? So this transform here says toTensor. If we have a look at the docstring, we got convert a pill image, which is what we're working with right now, or a NumPy array to a tensor. This transform does not support torch script. If you'd like to find out what that is, I'd like you to read the documentation for that. It's essentially turning your PyTorch code into a Python script. It converts a pill image or a NumPy array from height, width, color channels in the range 0 to 255, which is what our values are up here. They're from 0 to 255, red, green, and blue, to a torch float tensor of shape, color channels, height, width in the range 0 to 1. So it will take our tensor values here, or our NumPy array values, from 0 to 255 and convert them into a torch tensor in the range 0 to 1. We're going to see this later on in action, but this is our first transform. So we can pass data through that. In fact, I'd encourage you to try that out. See what happens when you pass in data transform. What happens when you pass it in our image as array? Image as array. Let's see what happens, hey? Oh, image should be pill image, got class NumPy array. What if we just pass in our straight up image? So this is a pill image. There we go, beautiful. So if we look at the shape of this, what do we get? 3, 64, 64. There's 64. And what if we wanted to change this to 224, which is another common value for computer vision models? 224, 224. Do you see how powerful this is, this little transforms module, the Torch Vision library? We'll change that back to 64, 64. And then if we have a look at what D type of our transform tensor is, we get torch float 32. Beautiful. So now we've got a way to transform our images into tensors. And so, but we're still only doing this with one image. How about we progress towards doing it for every image in our data folder here? But before we do that, I'd like to visualize what this looks like. So in the next video, let's write some code to visualize what it looks like to transform multiple images at a time. And I think it'd be a good idea to compare the transform that we're doing to the original image. So I'll see you in the next video. Let's write some visualization code. Let's now follow our Data Explorer's motto of visualizing our transformed images. So we saw what it looks like to pass one image through a data transform. And if we wanted to find more documentation on Torch Vision transforms, where could we go? There's a lot of these. So transforming and augmenting images, this is actually going to be your extra curriculum for this video. So transforms are common image transformations available in the transforms module. They can be chained together using compose, which is what we've already done. Beautiful. And so if you'd like to go through all of these, there's a whole bunch of different transforms that you can do, including some data augmentation transforms. And then if you'd like to see them visually, I'd encourage you to check out illustration of transforms. But let's write some code to explore our own transform visually first. So I'll leave this as a link. So I'll go up here, right here. Transforms help you get your images ready to be used with a model / perform data augmentation. Wonderful. So we've got a way to turn images into tensors. That's what we want for our model. We want our images as PyTorch tensors. The same goes for any other data type that you're working with. But now I'd just like to visualize what it looks like if we plot a number of transformed images. So we're going to make a function here that takes in some image paths, a transform, a number of images to transform at a time, and a random seed here because we're going to harness the power of randomness, and sometimes we want to set the seed, sometimes we don't. So we have an image path list that we've created before, which is just all of the image paths that we have of our data set. So data, pizza, steak, sushi. Now, how about we select some random image paths and then take the image from that path, run it through our data transform, and then compare the original image of what it looks like and the transformed image and what that looks like. Let's give it a try, hey? So I'm going to write a docstring of what this does, and then selects random images from a path of images and loads / transforms them, then plots the original versus the transformed version. So that's quite a long docstring, but that'll be enough. We could put in some stuff for the image paths, transforms, and seed. We'll just code this out. Let's go random seed. We'll create the seed. Or maybe we do it if seed, random seed. Let's put that. And we'll set seed to equal none by default. That way we can, we'll see if this works, hey? If in doubt, code it out. Random image paths, and then we're going to go random sample from the image paths and the number of sample that we're going to do. So random sample is going to, this will be a list. I'll just pass in here that this is a list. So we're going to randomly sample k, which is going to be n, so 3 images from our image path list. And then we're going to go for image path. We're going to loop through the randomly sampled image paths. You know how much I love harnessing the power of randomness for visualization. So for image path in random image paths, let's open up that image using pill. Image.open image path as f. And then we're going to create a figure and an axis. And we're going to create a subplot with matplotlib. So subplots, and we want it to create 1 row. So it goes n rows, n cols. 1 row and n cols equals 2. And then on the first, or the 0th axis, we're going to plot the original image. So imshow, we're just going to pass it straight in f. And then if we want to go ax0, we're going to set the title. So set title. We're going to set it to be the original. So we'll create this as an f string, original, and then new line, we'll create a size variable. And this is going to be f.size. So we're just getting the size attribute from our file. So we'll keep going and we'll turn off the axes here. So axis, and we're going to set that to false. Now let's transform on the first axis plot. We're going to transform and plot target image. This is so that our images are going to be side by side, the original and the transformed version. So there's one thing that we're going to have to do. I'll code it out in the wrong way first. I think that'll be a good way to illustrate what's going on. F, so I'm just going to put a note here. Note, we will need to change shape for matplotlib because we're going to come back here. Because what does this do? What have we noticed that our transform does? If we check the shape here, oh, excuse me, it converts our image to color channels first. Whereas matplotlib prefers color channels last. So just keep that in mind for when we're going forward. This code, I'm writing it, it will error on purpose. So transformed image, and then we're going to go ax1 as well. We're going to set the title, which is going to be transformed, and then we'll create a new line and we'll say size is going to be transformed image dot shape. Oh, probably a bit of, yeah, we could probably go shape here. And then finally, we're going to go ax1. We're going to turn the axis, we're going to set that to false. You can also set it to off. So you could write false or you could write off. You might see that, different versions of that somewhere. And I'm going to write a super title here, which we'll see what this looks like. Class is going to be image path. So we're getting the target image path, and we're just going to get the attribute or the parent attribute and then the stem attribute from that, just like we did before to get the class name. And then I'm going to set this to a larger font size so that we make some nice looking plots, right? If we're going to visualize our data, we might as well make our plots visually appealing. So let's plot some transformed data or transformed images. So image paths, we're going to set this to image path list, which is just the variable we have down below, which is a path list, a list containing all of our image paths. Our transform, we're going to set our transform to be equal to our data transform. So this just means that if we pass the transform in, our image is going to go through that transform and then go through all of these. It's going to be resized, it's going to be randomly horizontally flipped, and it's going to be converted to a tensor. And then, so we're going to set that data transfer there, or data transform, sorry. N is going to be 3, so we plot 3 images, and we'll set the seed to 42 to begin with. Let's see if this works. Oh, what did we get wrong? We have invalid shape. As I said, I love seeing this error because we have seen this error many times and we know what to do with it. We know that we have to rearrange the shapes of our data in some way, shape, or form. Wow, I said shape a lot there. That's all right. Let's go here, permute. This is what we have to do. We have to permute. We have to swap the order of the axes. So right now our color channels is first. So we have to bring this color channel axis or dimension to the end. So we need to shuffle these across. So 64 into here, 64 into here, and 3 on the end. We need to, in other words, turn it from color channels first to color channels last. So we can do that by permuting it to have the first axis come now in the 0 dimension spot. And then number 2 is going to be in the first dimension spot. And then number 0 is going to be at the back end. So this is essentially going from C, H, W, and we're just changing the order to be H, W, C. So the exact same data is going to be within that tensor. We're just changing the order of the dimensions. Let's see if this works. Woohoo! Look at that. Oh, I love seeing some manipulated data. We have a class of pizza and the original image is there and it's 512 by 512, but then we've resized it using our transform. Notice that it's a lot more pixelated now, but that makes sense because it's only 64 pixels. Now, why might we do such a thing? Well, one, is this image still look like that? Well, to me, it still does, but the most important thing will be, does it look like that to our model? Does it still look like the original to our model? Now, 64 by 64, there is less information encoded in this image. So our model will be able to compute faster on images of this size. However, we may lose some performance because not as much information is encoded as the original image. Again, the size of an image is something that you can control. You can set it to be a hyperparameter. You can tune the size to see if it improves your model. But I've just decided to go 64:3 in line with the CNN Explainer website. So a little hint, we're going to be re-replicating this model that we've done before. Now you notice that our images are now the same size, 64:3, as what the CNN Explainer model uses. So that's where I've got that from. But again, you could change this to size to whatever you want. And we see, oh, we've got a stake image here, and you notice that our image has been flipped on the horizontal. So the horizontal axis, our image has just been flipped, same with this one here. So this is the power of Torch transforms. Now there are a lot more transforms, as I said, You can go through them here to have a look at what's going on. Illustrations of transforms is a great place. So there's resize, there's center crop. You can crop your images. You can crop 5 different locations. You can do grayscale. You can change the color, a whole bunch of different things. I'd encourage you to check this out. That's your extra curriculum for this video. But now that we've visualized a transform, this is what I hinted at before, that we're going to use this transform for when we load all of our images into a Torch dataset. So I just wanted to make sure that they had been visualized first. We're going to use our data transform in the next video when we load all of our data using a torchvision.datasets helper function. So let's give that a go. I'll see you in the next video. Have a look at that beautiful plot. We've got some original images and some transformed images. And the beautiful thing about our transformed images is that they're in tensor format, which is what we need for our model. That's what we've been slowly working towards. We've got a data set, and now we've got a way to turn it into tensors, ready for a model. So let's just visualize what another... I'll turn the seed off here so we can look at some more random images. There we go. Okay, so we've got steak. Pixelated because we're downsizing 64:3. Same thing for this one, and it's been flipped on the horizontal. And then same thing for this pizza image, and we'll do one more to finish off. Wonderful. So that is the premise of transforms, turning our images into tensors and also manipulating those images if we want to. So let's get rid of this. I'm going to make another heading. We're up to section or part 4 now, and this is going to be option 1. So loading image data using image folder. And now I'm going to turn that into Markdown. And so let's go Torch Vision datasets. So recall how each one of the Torch Vision domain libraries has its own datasets module that has built-in functions for helping you load data. In this case, we have an image folder, and there's a few others here if you'd like to look into those. But an image folder, this class is going to help us load in data that is in this format, the generic image classification format. So this is a pre-built datasets function. Just like there's pre-built datasets, we can use pre-built dataset functions. Now, option 2 later on, this is a spoiler, is we're going to create our own custom version of a dataset loader, but we'll see that in a later video. So let's see how we can use image folder to load all of our custom data, our custom images, into tensors. So this is where the transform is going to come in helpful. So let's write here, we can load image classification data using, let's write the full path name, torchvision.datasets.image folder. Put that in there. Beautiful. And so let's just start it out. Use image folder to create datasets. And now in a previous video, I hinted at the fact that we can pass a transform to our image folder class. That's going to be right here. So let's see what that looks like in practice. So from Torch Vision, I'm going to import datasets because that's where the image folder module lives. And then we can go train data equals datasets.image folder. And we're going to pass in the root, which is our train dir, because we're going to do it for the training directory first. And then we're going to pass in a transform, which is going to be equal to our data transform. And then we're going to pass in a target transform, but we're going to leave this as none, which is the default, I believe. If we go up to here, yeah, target transform is optional. So what this means is this is going to be a transform for the data, and this is going to be a transform for the label / target. PyTorch likes to use target, I like to use label, but that's okay. So this means that we don't need a target transform because our labels are going to be inferred by the target directory where the images live. So our pizza images are in this directory and they're going to have pizza as the label because our data set is in standard image classification format. Now, if your dataset wasn't in standard image classification format, you might use a different data loader here. A lot of them will have a transform for the data. So this transform is going to run our images, whatever images are loaded from these folders, through this transform that we've created here. It's going to resize them, randomly flip them on the horizontal, and then turn them into tensors, which is exactly how we want them for our PyTorch models. And if we wanted to transform the labels in some way, shape, or form, we could pass in a target transform here. But in our case, we don't need to transform the labels. So let's now do the same thing for the test data. And so that's why I wanted to visualize our transforms in the previous videos, because otherwise we're just passing them in as a transform. So really what's going to happen behind the scenes is all of our images are going to go through these steps. And so that's what they're going to look like when we turn them into a data set. So let's create the tester here, or the test data set. The transform, we're going to transform the test data set in the same way we've transformed our training data set. And we're just going to leave that like that. So let's now print out what our data sets look like. Train data and test data. Beautiful. So we have a data set, a Torch data set, which is an image folder, and we have number of data points. This is going to be for the training data set. We have 225, so that means about 75 images per class. And we have the root location, which is the folder we've loaded them in from, which is our training directory. We've set these two up before, trained-er and test-er. And then we have a transform here, which is a standard transform, a resize, followed by a random horizontal flip, followed by to tensor. Then we've got basically the same output here for our test directory, except we have less samples there. So let's get a few little attributes from the image folder. This is one of the benefits of using a PyTorch pre-built data loader, or dataset loader, is that it comes with a fair few attributes. So we could go to the documentation, find this out from in here, inherits from dataset folder, keep digging into there, or we could just come straight into Google Colab. Let's go get class names as a list. Can we go train data dot and then press tab? Beautiful. So we've got a fair few things here that are attributes. Let's have a look at classes. This is going to give us a list of the class names. Class names. This is very helpful later on. So we've got pizza, steak, sushi. We're trying to do everything with code here. So if we have this attribute of traindata.classes, we can use this list later on for when we plot images straight from our data set or make predictions on them and we want to label them. You can also get class names as a dictionary mapped to their integer index, that is. So we can go train data dot and press tab. We've got class to IDX. Let's see what this looks like. Class dict. Wonderful. So then we've got our string class names mapped to their integer. So we've got pizza is 0, steak is 1, sushi is 2. Now, this is where the target transform would come into play. If you wanted to transform these labels here in some way, shape, or form, you could pass a transform into here. And then if we keep going, let's check the lengths of what's going on. Check the lengths of our data set. So we've seen this before, but this is going to just give us how many samples that we have. Length, train data, length, test data. Beautiful. And then of course, if you'd like to explore more attributes, you can go train data dot, and then we've got a few other things, functions, images, loader, samples, targets. If you wanted to just see the images, you can go dot samples. If you wanted to see just the labels, you can go dot targets. This is going to be all of our labels. Look at that. And I believe they're going to be in order. So we're going to have 0, 0, 0, 1, 1, 1, 2, 2, 2. And then if we wanted to have a look, let's say we have a look at the first sample, hey? We have data, pizza, steak, sushi, train, pizza. There's the image path, and it's a label 0 for pizza. Wonderful. So now we've done that, how about we've been visualizing this whole time. So let's keep up that trend. And let's visualize a sample and a label from the train data dataset. So in this video, we've used image folder, to load our images into tensors. And because our data is already in standard image classification format, we can use one of TorchVision.Datasets pre-built functions. So let's do some more visualization in the next video. I'll see you there. Welcome back. In the last video, we used datasets.image folder to turn all of our image data into tensors. And we did that with the help of our data transform, which is a little pipeline up here to take in some data, or specifically an image, resize it to a value that we've set, in our case 6464, randomly flip it along the horizontal. We don't necessarily need this, but I've just put that in there to indicate what happens when you pass an image through a transforms pipeline. And then most importantly, we've turned our images into a Torch tensor. So that means that our data, our custom data set, this is so exciting, is now compatible to be used with a PyTorch model. So let's keep pushing forward. We're not finished yet. We're going to visualize some samples from the trained data dataset. So how can we do this? We can index on the trained data dataset to get a single image and a label. So if we go, can we do train data 0? What does that give us? Okay, so this is going to give us an image tensor and its associated label. In this case, it's an image of pizza, because why? Its associated label is pizza. So let's take the 0th 0. So this is going to be our image, and the label is going to be train data 0, and we're just going to get the first index item there, which is going to be 1. And then if we have a look at them separately, image and label, beautiful. So now one of our target images is in tensor format, exactly how we want it, and its label is in numeric format as well, which is also exactly how we want it. And then if we wanted to convert this back to a non-label, we can go class names and index on that, and we see pizza. And I mean, non-label is in non-numeric. We can get it back to string format, which is human understandable. We can just index on class names. So let's print out some information about what's going on here. Print f, we're going to go image tensor. I love f strings if you haven't noticed yet. Image tensor, and we're going to set in new line. We're going to pass it in our image, which is just the image that we've got here. Then we'll print in some more information about that. This is still all becoming one with the data, right? We're slowly finding out information about our data set so that if errors arise later on, we can go, our image, or we're getting a shape error, and I know our images are of this shape, or we're getting a data type error, which is why I've got the .d type here, and that might be why we're getting a data type issue. So let's do one more with the image label. Oh, well actually, we'll do one more. We'll do print, we'll get the label data type as well. Label, this will be important to take note of later on. Type, as I said, 3 big issues: shape mismatch, device mismatch, and data type mismatch. Can we get the type of our label? Beautiful. So we've got our image tensor, and we've got its shape. It's of torch size 36464. That's exactly how we want it. The data type is torch float 32, which is the default data type in PyTorch. Our image label is 0, and the label data type is of integer. So let's try and plot this and see what it looks like, hey? Using matplotlib. So first of all, what do we have to do? Well, we have to rearrange the order of dimensions. In other words, matplotlib likes color channels last. So let's see what this looks like. We'll go image permute. We've done this before. Image.permute 1, 2, 0 means we're reordering the dimensions. 0 would usually be here, except that we've taken the 0th dimension, the color channels, and put it on the end and shuffled the other 2 forward. So let's now print out different shapes. I love printing out the change in shapes. It helps me really understand what's going on, because sometimes I look at a line like this and it doesn't really help me, but if I print out something of what the shapes were originally and what they changed to, well, hey, that's a big help. That's what Jupyter Notebooks are all about, right? So this is going to be color channels first, height, width, and depending on what data you're using, if you're not using images, if you're using text, still knowing the shape of your data is a very good thing. We're going to go image permute.shape, and this should be, everything going right, is height, width, color channels on the end here. And we're just going to plot the image. Can never get enough plotting practice. Plot the image. We're going to go plt.figure. We'll pass in fig size equals 10.7. And then we're going to go plt.imshow. We'll pass in the permuted image, image underscore permutes, and then we'll turn off the axes, and we will set the title to be class names, and we're going to index on the label just as we did before, and we're going to set the font size equal to 14 so it's nice and big. Here we go. Beautiful. There is our image of pizza. It is very pixelated because we're going from about 512 as the original size, 512 by 512 to 6464. I would encourage you to try this out. Potentially you could use a different image here. So we've indexed on sample 0. Maybe you want to change this to just be a random image and go through these steps here. And then if you'd like to see different transforms, I'd also encourage you to try changing this out, our transform pipeline here. Maybe increase the size and see what it looks like. And if you're feeling really adventurous, you can go into Torch Vision and look at the transforms library here and then try one of these and see what it does to our images. But we're going to keep pushing forward. We are going to look at another way, or actually, I think for completeness, let's now turn, we've got a data set. We wrote up here before that we wanted to turn our images into a data set and then subsequently a Torch utils data loader. So we've done this before by batching our images or batching our data that we've been working with. So I'd encourage you to give this a shot yourself. Try to go through the next video and create a train data loader using our train data, wherever that is, train data, and a test data loader using our test data. So give that a shot and we'll do it together in the next video. We'll turn our data sets into data loaders. Welcome back. How'd you go? In the last video, I issued you the challenge to turn our data sets into data loaders. So let's do that together now. I hope you gave it a shot. That's the best way to practice. So turn loaded images into data loaders. So we're still adhering to our PyTorch workflow here. We've got a custom data set. We found a way to turn it into tensors in the form of data sets. And now we're going to turn it into a data loader so we can turn our data sets into iterables or batchify our data. So let's write down here, a data loader is going to help us turn our data sets into iterables. And we can customize the batch size, write this down, so our model can see batch size images at a time. So this is very important. As we touched on in the last section, computer vision, we create a batch size because if we had 100,000 images, chances are if they were all in one data set, there's 100,000 images in the Food 101 data set, we're only working with about 200. If we tried to load all 100,000 in one hit, chances are our hardware may run out of memory. And so that's why we batchify our images. So if we have a look at this, NVIDIA SMI, our GPU only has 16 gigabytes. I'm using a Tesla T4 right now. Well, it has about 15 gigabytes of memory. So if we tried to load 100,000 images into that, whilst also computing on them with a PyTorch model, potentially we're going to run out of memory and run into issues. So instead, we can turn them into a data loader so that our model looks at 32 images at a time and can leverage all of the memory that it has rather than running out of memory. So let's turn our train and test data sets into data loaders. Turn train and test data sets into data loaders. Now, this is not just for image data. This is for all kinds of data in PyTorch. Images, text, audio, you name it. So import data loader, then we're going to create a train data loader. We're going to set it equal to data loader. We're going to pass in a data set. So let's set this to train data. Let's set the batch size. What should we set the batch size to? I'm going to come up here and set it as a capital variable. I'm going to use 32 because 32 is a good batch size. So we'll go 32, or actually, let's start small. Let's just start with a batch size of 1 and see what happens. Batch size 1, number of workers. So this parameter is going to be, this is an important one. I potentially have covered it before, but I'm going to introduce it again. Is this going to be how many cores or how many CPU cores that is used to load your data? So the higher the better usually, and you can set this via OS CPU count, which will count how many CPUs your compute hardware has. So I'll just show you how this works. Import OS, and this is a Python OS module. We can do CPU count to find out how many CPUs our Google Colab instance has. Mine has 2. Your number may vary, but I believe most Colab instances have 2 CPUs. If you're running this on your local machine, you may have more. If you're running it on dedicated deep learning hardware, you may even have even more, right? So generally, if you set this to 1, it will use 1 CPU core, but if you set it to os.cpu count, it will use as many as possible. So we're just going to leave this as 1 right now. You can customize this to however you want. And I'm going to shuffle the training data because I don't want my model to recognize any order in the training data, so I'm going to mix it up. And then I'm going to create the test data loader. Dataset equals test data, and batch size equals 1. Num workers, I'm going to set this to equal 1 as well. Again, you can customize each of these. They're hyperparameters to whatever you want. Number of workers, generally the more the better. And then I'm going to set shuffle equals false for the test data so that if we want to evaluate our models later on, our test data set is always in the same order. So now let's have a look at train data loader, see what happens, and test data loader. Wonderful. So we get 2 instances of torch utils.data.dataloader, and now we can see if we can visualize something from the train data loader as well as the test data loader. Or actually, maybe we'll just visualize something from one of them so we're not just double handling everything. Do we get a length here? Wonderful. Because we're using a batch size of 1, our lengths of our data loaders are the same as our data sets. Now, of course, this would change if we set, we didn't even set this to the batch size parameter. Batch size. Let's come down here and do the same here. Batch size. So we'll watch this change. If we wanted to look at 32 images at a time, we definitely could do that. So now we have 8 batches because 225 divided by 32 equals roughly 8. And then 75 divided by 32 also equals roughly 3. And remember, these numbers are going to be rounded if there are some overlaps. So let's get rid of, we'll change this back to 1. And we'll keep that there. We'll get rid of these 2. And let's see what it looks like to plot an image from our data loader. Or at least have a look at it. Check out the shapes. That's probably the most important point at this time. We've already plotted enough things. So let's iterate through our train data loader, and we'll grab the next one. We'll grab the image and the label, and we're going to print out here. So batch size will now be 1. You can change the batch size if you like. This is just, again, another way of getting familiar with the shapes of our data. So image shape. Let's go image.shape, and we're going to write down here, this shape is going to be batch size. This is what our data loader is going to add to our images. It's going to add a batch dimension. Color channels, height, width, and then print. Let's check out the label shape. Same thing with the labels. It's going to add a batch dimension. Label, and let's see what happens. Oh, we forgot the end of the bracket. Beautiful. So we've got image shape. Our label shape is only 1 because we have a batch size of 1. And so now we've got batch size 1, color channels 3, height, width. And if we change this to 32, what do you think is going to happen? We get a batch size of 32, still 3 color channels, still 64, and now we have 32 labels. So that means within each batch, we have 32 images and we have 32 labels. We could use this with a model. I'm going to change this back to 1. And I think we've covered enough in terms of loading our data sets. How cool is this? We've come a long way. We've downloaded a custom data set. We've loaded it into a data set using image folder, turned it into tensors using our data transform, and now batchified our custom data set in DataLoaders. We've used these with models before. So if you wanted to, you could go right ahead and build a convolutional neural network to try and find patterns in our image tensors. But in the next video, let's pretend we didn't have this data loader, this image folder class available to us. How could we load our image data set so that it's compatible, like our image data set here? How could we replicate this image folder class so that we could use it with a data loader? Because DataLoaders is part of Torch utils.data. You're going to see these everywhere. Let's pretend we didn't have the Torch vision.datasets image folder helper function. And we'll see in the next video how we can replicate that functionality. I'll see you there. Welcome back. So over the past few videos, we've been working out how to get our data from our data folder, pizza, steak, and sushi. We've got images of different food data here, and we're trying to get it into tensor format. So we've seen how to do that with an existing data loader helper function or a dataset function in image folder. However, what if image folder didn't exist and we needed to write our own custom data loading function? Now, the premise of this is, although it does exist, it's going to be good practice because you might come across a case where you're trying to use a dataset where a pre-built function doesn't exist. So let's replicate the functionality of image folder by creating our own data loading class. So we want a few things. We want to be able to get the class names as a list from our loaded data, and we want to be able to get our class names as a dictionary as well. So the whole goal of this video is to start writing a function or a class that's capable of loading data from here into tensor format, capable of being used with the PyTorch's data loader class like we've done here. So we want to create a data set. Let's start it off. We're going to create another heading here. This is going to be number 5, option 2. Loading image data with a custom data set. So we want a few functionality steps here. Number 1 is want to be able to load images from file. 2, want to be able to get class names from the data set. And 3, want to be able to get classes as dictionary from the data set. And so let's briefly discuss the pros and cons of creating your own custom data set. We saw option 1 was to use a pre-existing dataset loader helping function from Torch Vision. And it's going to be quite similar if we go Torch Vision datasets. Quite similar if you're using other domain libraries here. They were going to be data loading utilities. But at the base level of PyTorch is Torch utils.data.dataset. Now this is the base dataset class. So we want to build on top of this to create our own image folder loading class. So what are the pros and cons of creating your own custom data set? Well, let's discuss some pros. So one pro would be you can create a data set out of almost anything as long as you write the right code to load it in. And another pro is that you're not limited to PyTorch pre-built dataset functions. A couple of cons would be that even though this is to point number 1, so even though you could create a data set out of almost anything, it doesn't mean that it will automatically work. It will work. And of course, you can verify this through extensive testing, seeing if your model actually works, if it actually loads data in the way that you want it. And another con is that using a custom data set requires us to write more code. So often results in us writing more code, which could be prone to errors or performance issues. So typically, if something makes it into the PyTorch standard library or the PyTorch domain libraries, if functionality makes it into here, it's generally been tested many, many times, and it can kind of be verified that it works quite well with, well, if you do use it, it works quite well. Whereas if we write our own code, sure, we can test it ourselves, but it hasn't got the robustness to begin with, that is, we could fix it over time, as something that's included in, say, the PyTorch standard library. Nonetheless, it's important to be aware of how we could create such a custom data set. So let's import a few things that we're going to use. We'll import OS because we're going to be working with Python's file system over here. We're going to import pathlib because we're going to be working with file paths. We'll import torch. We don't need to again, but I'm just doing this for completeness. We're going to import image from pill, the image class, because we want to be opening images. I'm going to import from torch utils.data. I'm going to import dataset, which is the base dataset. And as I said over here, we can go to datasets, click on torch utils data.dataset. This is an abstract class representing a dataset. And you'll find that this dataset links to itself. So this is the base dataset class. Many of the datasets in PyTorch, the pre-built functions, subclass this. So this is what we're going to be doing it. And there's a few notes here. All subclasses should overwrite getItem, and you should optionally overwrite len. These two methods. We're going to see this in a future video. For now, we're just setting the scene here. So from Torch Vision, we're going to import transforms because we want to not only import our images, but we want to transform them into tensors. And from the Python's typing module, I'm going to import tuple, dict, and list so we can put type hints when we create our class and loading functions. Wonderful. So this is our instance of torch vision.datasets image folder, torch vision.datasets.image folder. Let's have a look at the train data. So we want to write a function that can replicate getting the classes from a particular directory and also turning them into an index or dictionary, that is. So let's build a helper function to replicate this functionality here. In other words, I'd like to write a helper function that if we pass it in a file path, such as pizza steak sushi or this data folder, it's going to go in here and it's going to return the class names as a list, and it's also going to turn them into a dictionary, because it's going to be helpful for later on when we'd like to access the classes and the class to IDX. And if we really want to completely recreate image folder, well, image folder has this functionality, so we'd like that too. So this is just a little high-level overview of what we're going to be doing. I might link in here that we're going to subclass this. So all custom datasets in PyTorch often subclass this. So here's what we're going to be doing. Over the next few videos, we want to be able to load images from a file. Now you could replace images with whatever data that you're working with. The same premise will be here. You want to be able to get the class names from the dataset and want to be able to get classes as dictionary from the dataset. So we're going to map our samples, our image samples, to their class name by just passing a file path to a function that we're about to write. And some pros and cons of creating a custom data set. We've been through that. Let's in the next video start coding up a helper function to retrieve these two things from our target directory. In the last video, we discussed the exciting concept of creating a custom data set. And we wrote down a few things that we want to get. we discussed some pros and cons, and we learned that many custom datasets inherit from torch.utils.data.dataset. So that's what we'll be doing later on. In this video, let's focus on writing a helper function to recreate this functionality. So I'm going to title this 5.1, creating a helper function to get class names. I'm going to turn this into Markdown. And if I go into here, so we want a function to, let's write down some steps and then we'll code it out. So we'll get the class names. We're going to use os.scandir. So it's going to scan a directory to traverse a target directory. And ideally, the directory is in standard image classification format. So just like the image folder class, our custom data class is going to require our data already be formatted in the standard image classification format, such as train and test for training and test images, and then images for a particular class are in a particular directory. So let's keep going. And number 2, what else do we want it to do? We want it to raise an error if the class names aren't found. So if this happens, there might be, we want this to hint at the fact that there might be something wrong with the directory structure. And number 3, we also want to turn the class names into a dict and a list and return them. Beautiful. So let's get started. Let's set up the path directory for the target directory. So our target directory is going to be what? The directory we want to load, directory, if I could spell, we want to load our data from. Let's start with the training dir, just for an example. So target directory, what do we get? So we're just going to use the training folder as an example to begin with. And we'll go print target dir, we'll put in the target directory. Just want to exemplify what we're doing. And then we're going to get the class names from the target directory. So I'll show you the functionality of os.scandir. Of course, you could look this up in the Python documentation. So class names found, let's set this to be sorted, and then we'll get the entry name, entry.name for entry in list. So we're going to get os list scandir of the image path / target directory. Let's see what happens when we do this. Target directory, have we got the right brackets here? Is this going to work? Let's find out. Oh, image path / target directory. What did we get wrong? Oh, we don't need the image path there. Let's just put target directory there. There we go. Beautiful. So we set up our target directory as being the training dir. And so if we just go, let's just do list. What happens if we just run this function here? os.scandir. Yeah, so there we go. So we have 3 directory entries. So this is where we're getting entry.name for everything in the training directory. So if we look in the training directory, what do we have? Train. And we have 1 entry for pizza, 1 entry for sushi, 1 entry for steak. Wonderful. So now we have a way to get a list of class names. And we could quite easily turn this into a dictionary, couldn't we? Which is exactly what we want to do. We want to recreate this, which we've done, and we want to recreate this, which is also done. So now let's take this functionality here, and let's turn that into a function. All right, what can we do? What do we call this? I'm going to call this define classes, and I'm going to say that it takes in a directory which is a string, and it's going to return, this is where I imported typing from Python typing. I imported tuple, and I'm going to return a list, which is a list of strings, and a dictionary, which is strings mapped to integers. Beautiful. So let's keep going. We want this function to return, given a target directory, we want it to return these 2 things. So we've seen how we can get a list of the directories in a target directory by using os-scan-dir. So let's write finds the classes, the class folder names in a target directory. Beautiful. And we know that it's going to return a list and a dictionary. So let's do step number 1. We want to get the class names by scanning the target directory. We'll go classes. We're going to replicate the functionality we've done above, but for any given directory here. So classes equals sorted entry.name for entry in os-scan-dir, and we're going to pass it the target directory if entry.isdir. We're just going to make sure it's a directory as well. And so if we just return classes and see what happens. So find classes, let's pass it in our target directory, which is our training directory. What do we get? Beautiful. So we need to also return class to IDX. So let's keep going. So number 2 is let's go raise an error if class names could not be found. So if not classes, let's say raise file, we're going to raise a file not found error. And then let's just write in here, F couldn't find any classes in directory. So we're just writing some error checking code here. So if we can't find a class list within our target directory, we're going to raise this error and say couldn't find any classes in directory. Please check file structure. And there's another check up here that's going to help us as well to check if the entry is a directory. So finally, let's do number 3. What do we want to do? So we want to create a dictionary of index labels. So computers, why do we do this? Well, computers prefer numbers rather than strings as labels. So we can do this. We've already got a list of classes. So let's just create class to IDX equals class name I for I class name in enumerate classes. Let's see what this looks like, hey? So we'll go class names and then class to IDX, or we can just return it actually. Do we spell enumerate wrong? Yes, we did. So what this is going to do is going to map a class name to an integer, or to I, for I class name in enumerate classes. So it's going to go through this, and it's going to go for I. So the first one, 0, is going to be pizza, ideally. 1 will be steak, 2 will be sushi. Let's see how this goes. Beautiful, look at that. We've just replicated the functionality of image folder. So now we can use this helper function in our own custom dataset, find classes, to traverse through a target directory such as train. We could do the same for test if we wanted to too. And that way, we've got a list of classes, and we've also got a dictionary mapping those classes to integers. So now, let's in the next video move towards subclassing torch utils.data.dataset, and we're going to fully replicate image folder. So I'll see you there. In the last video, we wrote a great helper function called find classes that takes in a target directory and returns a list of classes and a dictionary mapping those class names to an integer. So let's move forward, and this time we're going to create a custom dataset to replicate image folder. Now we don't necessarily have to do this, right? Because image folder already exists, and if something already exists in the PyTorch library, chances are it's going to be tested well, it's going to work efficiently, and we should use it if we can. But if we needed some custom functionality, we can always build up our own custom dataset by subclassing torch.utils.data.dataset, or if a pre-built dataset function didn't exist, well, we're probably going to want to subclass torch.utils.data.dataset anyway. And if we go into the documentation here, there's a few things that we need to keep in mind when we're creating our own custom dataset. All datasets that represent a map from keys to data samples, so that's what we want to do. We want to map keys, in other words, targets or labels, to data samples, which in our case are food images. So we should subclass this class here. Now, to note, all subclasses should overwrite getItem. So getItem is a method in Python, which is going to get an item or get a sample, supporting fetching a data sample for a given key. So for example, if we wanted to get sample number 100, this is what getItem should support. It should return us sample number 100. And subclasses could also optionally override len, which is the length of a dataset. So return the size of the dataset by many sampler implementations and the default options of DataLoader, because we want to use this custom dataset with DataLoader later on. So we should keep this in mind when we're building our own custom subclasses of Torch utils data.dataset. Let's see this hands-on. We're going to break it down. It's going to be a fair bit of code, but that's all right. Nothing that we can't handle. So to create our own custom dataset, we want to, number one, first things first is we're going to subclass torch.utils.data.dataset. Two, what do we want to do? We want to init our subclass with a target directory. So the directory we'd like to get data from, as well as a transform if we'd like to transform our data. So just like when we used image folder, we could pass a transform to our dataset so that we could transform the data that we were loading. We want to do the same thing, and we want to create several attributes. Let's write them down here. We want paths, which will be the paths of our images. What else do we want? We want transform, which will be the transform we'd like to use. We want classes, which is going to be a list of the target classes. And we want class to IDX, which is going to be a dict of the target classes mapped to integer labels. Now, of course, these attributes will differ depending on your data set, but we're replicating image folder here. So these are just some of the things that we've seen that come with image folder. But regardless of what data set you're working with, there are probably some things that you want across them universal. You probably want all the paths of where your data is coming from, the transforms you'd like to perform on your data, what classes you're working with, and a map of those classes to an index. So let's keep pushing forward. We want to create a function to load images, because after all, we want to open some images. So this function will open an image. Number 5, we want to overwrite the len method to return the length of our dataset. So just like it said in the documentation, if you subclass using torch.utils.data.dataset, you should overwrite getItem, and you should optionally overwrite len. So we're going to, instead of optionally, we are going to overwrite length. And number 6, we want to overwrite the getItem method to return a given sample when passed an index. Excellent. So we've got a fair few steps here, but if they don't make sense now, it's okay. Let's code it out. Remember our motto, if in doubt, code it out. And if in doubt, run the code. So we're going to write a custom data set. This is so exciting because when you work with pre-built data sets, it's pretty cool in machine learning. But when you can write code to create your own data sets, and that's magic. So number 1 is we're going to, number 0 is we're going to import Torch utils dataset. We don't have to rewrite this, we've already imported it, but we're going to do it anyway for completeness. Now, step number 1 is to subclass it. Subclass torch utils dataset. So just like when we built a model, we're going to subclass and then module, but in this time we're going to call our class image folder custom, and we're going to inherit from dataset. This means that all the functionality that's contained within Torch Utils dataset, we're going to get for our own custom class. Number 2, let's initialize. So we're going to initialize our custom dataset. And there's a few things that we'd like. Init our subclass with the target directory, the directory we'd like to get data from, as well as a transform if we'd like to transform our data. So let's write a init function, init, and we're going to go self targdir, and targdir is going to be a string, and we're going to set a transform here. We'll set it equal to none. Beautiful. So this way we can pass in a target directory of images that we'd like to load, and we can also pass in a transform, just similar to the transforms that we've created previously. So now we're up to number 3, which is create several attributes. So let's see what this looks like. Create class attributes. So we'll get all of the image paths. So we can do this just like we've done before. Self paths equals list pathlib.path, because what's our target directory going to be? Well, I'll give you a spoiler alert. It's going to be a path like the test directory, or it's going to be the train directory, because we're going to use this once for our test directory and our train directory, just like we used the original image folder. So we're going to go through the target directory and find out all of the paths. So this is getting all of the image paths that support or that follow the file name convention of */star.jpg. So if we have a look at this, if we passed in the test folder, so test is the folder, star would mean any of these, 1, 2, 3, pizza, steak, sushi, that's the first star. Then slash would go into the pizza directory. The star here would mean any of the file combinations here that end in .jpg. So this is getting us a list of all of the image paths within a target directory. In other words, within the test directory and within the train directory when we call these two separately. So let's keep going. We've got all of the image paths. What else did we have to do? We want to create transforms. So let's set up transforms. Self.transforms equals transform. Oh, we'll just call that transform actually. Set up transform equals transform. So we're going to get this from here. And I put it as none because transform can be optional. So let's create classes and class to IDX attributes, which is the next one on our list, which is here, classes and class to IDX. Now, lucky us, in the previous video, we created a function to return just those things. So let's go self.classes and self.class to IDX equals find classes. And we're going to pass in the target dir, or the targ dir from here. Now, what's next? We've done step number 3. We need number 4 is create a function to load images. All right, let's see what this looks like. So number 4, create a function to load images. So let's call it load image, and we're going to pass in self, and we'll also pass in an index. So the index of the image we'd like to load, and this is going to return an image.image. So where does that come from? Well, previously we imported from pill. So we're going to use Python image library or Pillow to import our images. So we're going to, given a file path from here, such as pizza, we're going to import it with the image class. And we can do that using, I believe it's image.open. So let's give that a try. I'll just write a note in here. Opens an image via a path and returns it. So let's write image path equals self. This is why we got all of the image paths above. So self.paths, and we're going to index it on the index. Beautiful. And then let's return image.open image path. So we're going to get a particular image path, and then we're just going to open it. So now we're up to step number 5, override the len method to return the length of our data set. This is optional, but we're going to do it anyway. So overwrite len. So this just wants to return how many samples we have in our data set. So let's write that, def len. So if we call len on our data set instance, it's going to return just how many numbers there are. So let's write this down. Returns the total number of samples. And this is just going to be simply return length or len of self.paths. So for our target directory, if it was the training directory, we'd return the number of image paths that this code has found out here. And same for the test directory. So next, we're going to go, number 6 is we want to overwrite, we put this up here, the getItem method. So this is required if we want to subclass torch utils data dataset. So this is in the documentation here. All subclasses should override getItem. So we want getItem to, if we pass it an index to our dataset, we want it to return that particular item. So let's see what this looks like. Override the getItem method to return a particular sample. And now this method is going to leverage getItem, all of the code that we've created above. So this is going to go take in self, which is the class itself, and it's going to take in an index, which will be of an integer, and it's going to return a tuple of torch.tensor and an integer, which is the same thing that gets returned when we index on our training data. So if we have a look, image label equals train data 0, getItem is going to replicate this. If we pass it an index here, let's check out the image and the label. This is what we have to replicate. So remember, train data was created with image folder from torchvision.datasets. And so we want our getItem to return an image and a label, which is a tuple of a torch tensor, where the image is of a tensor here, and the label is of an integer, which is the label here, the particular index as to which this image relates to. So let's keep pushing forward. I'm going to write down here, returns one sample of data and label, x and, well, we'll just go xy, so we know that it's a tuple. Beautiful. So let's set up the image. What do we want the image to be? Well, this is where we're going to call on our self.loadImage function, which is what we've created up here. Do you see the customization capabilities of creating your own class? So we've got a fair bit of code here, right? But essentially all we're doing is we're just creating functions that is going to help us load our images into some way, shape, or form. Now, again, I can't stress this enough. Regardless of the data that you're working on, the pattern here will be quite similar. You'll just have to change the different functions you use to load your data. So let's load an image of a particular index. So if we pass in an index here, it's going to load in that image. Then what do? Well, we want to get the class name, which is going to be self.paths, and we'll get the index here, and we can go parent.name. So this expects path in format data folder / class name / image.jpg. That's just something to be aware of. And the class IDX is going to be self.class to IDX, and we will get the class name here. So now we have an image by loading in the image here. We have a class name because our data is going to be, or our data is currently in standard image classification format. You may have to change this depending on the format your data is in. We can get the class name from that, and we can get the class IDX by indexing on our attribute up here, our dictionary of class names to indexes. Now, we have one small little step. This is transform if necessary. So remember our transform parameter up here. If we want to transform our target image, well, let's put in if self.transform. If the transform exists, let's pass the image through that transform. Transform image, and then we're going to also return the class IDX. So do you notice how we've returned a tuple here? This is going to be a torch tensor if our transform exists, and the class IDX is also going to be returned, which is what we want here, X and Y, which is what gets returned here. Image as a tensor, label as an integer. So return data label X, Y, and then if the transform doesn't exist, let's just return image class IDX. Return untransformed image and label. Beautiful. So that is a fair bit of code there. So you can see the pro of subclassing torch utils data.dataset is that we could customize this in almost any way we wanted to load whatever data that we're working with, well, almost any data. However, because we've written so much code, this may be prone to errors, which we're going to find out in the next video to see if it actually works. But essentially all we've done is we've followed the documentation here, torch.utils data.dataset, to replicate the functionality of an existing data loader function, namely image folder. So if we scroll back up, ideally, if we've done it right, we should be able to write code like this, passing in a root directory, such as a training directory, a particular data transform, and we should get very similar instances as image folder, but using our own custom dataset class. So let's try that out in the next video. So now we've got a custom image folder class that replicates the functionality of the original image folder data loader class, or dataset class that is. Let's test it out. Let's see if it works on our own custom data. So we're going to create a transform here so that we can transform our images, raw JPEG images, into tensors, because that's the whole goal of importing data into PyTorch. So let's set up a train transforms compose. We're going to set it to equal to transforms.compose, and I'm going to pass in a list here that it's going to be transforms. We're going to resize it to 64, whatever the image size. We'll reduce it down to 64. Then we're going to go transforms.random horizontal flip. We don't need to necessarily flip them, but we're going to do it anyway just to see if it works. And then let's put in here transforms.toTensor, because our images are getting opened as a pill image using image.open, but now we're using the toTransform from PyTorch or Torch Visions.transforms. So I'll just put this here from torchvision.transforms. That way you know we're importing transforms there. And let's create one for the test data set as well, test transforms. We'll set this up. Oh, excuse me. We'll need to just go import transforms. And let's go transforms.compose. And we'll pass in another list. We're going to do the exact same as above. We'll set up resize, and we'll set the size equal to 64. And then transforms, we're going to go .toTensor. We're going to skip the data augmentation for the test data, because typically you don't manipulate your test data in terms of data augmentation. You just convert it into a tensor rather than manipulate its orientation, shape, size, etc. So let's run this. And now let's see how image folder custom class works. Test out image folder custom. Let's go, we'll set up the train data custom is equal to image folder custom, and then we'll set up the tag.dir, which is equal to the training directory, and then we'll pass in the transform, which is equal to the train transforms, which we just created above, train transforms. And then we're going to, I think that's all we need actually. We only had 2 parameters there. We're not going to use a target transform because our labels, we've got a helper function to transform our labels. So test data custom is going to be image folder custom, and I'm going to set up the tag to be equal to the test directory, and the transform is going to be the test transforms from the cell above there. And what's Colab telling me there? Oh, I'm going to set that up. Did we spell something? Oh, we spelled it wrong. Train transforms. There we go. Beautiful. Now let's have a look at our train data and test data custom. See if it worked. What do we have? Oh, we have an image folder custom. Well, it doesn't give us as much rich information as just checking it out as it does for the train data, but that's okay. We can still inspect these. So this is our original one made with image folder, and we've got now train data custom and test data custom. Let's see if we can get some information from these. So let's check the original length of the train data and see if we can use the len method on our train data custom. Did that work? Wonderful. Now how about we do it for the original test data made with image folder and our custom version made with test data or image folder custom. Beautiful. That's exactly what we want. And now let's have a look at the train data custom. Let's see if the classes attribute comes up. Dot classes, and we'll just leave that there. We'll do the class.idx. Yes, it is. So this attribute here is, I wonder if we get information from Google Colab. Loading. What do we get? Oh, classes to IDX, classes, load image, paths, transform. So if we go back up here, all these attributes are from here. Paths, transform, classes, class to IDX, as well as load image. So this is all coming from the code that we wrote, our custom dataset class. So let's keep pushing forward. Let's have a look at the class to IDX. Do we get the same as what we wanted before? Yes, we do. Beautiful. A dictionary containing our string names and their integer associations. So let's now check for equality. We can do this by going check for equality between original image folder dataset and image folder custom dataset. Now we've kind of already done that here, but let's just try it out. Let's go print. Let's go train data custom dot classes. Is that equal to train? Oh, I don't want 3 equals. Train data, the original one dot classes, and also print. Let's do test data custom dot classes. Is this equal to test data, the original one, classes? True and true. Now you could try this out. In fact, it's a little exercise to try it out to compare the others, but congratulations to us. We have replicated the main functionality of the image folder dataset class. And so the takeaways from this is that whatever data you have, PyTorch gives you a base dataset class to inherit from, and then you can write a function or a class that somehow interacts with whatever data you're working with. So in our case, we load in an image, and then you, as long as you override the len method and the getItem method and return some sort of values, well, you can create your own dataset loading function. How beautiful is that? So that's going to help you work with your own custom datasets in PyTorch. So let's keep pushing forward. We've seen analytically that our custom dataset is quite similar to the original PyTorch torchvision.datasets image folder dataset. But you know what I like to do? I like to visualize things. So let's in the next video create a function to display some random images from our train data custom class. It's time to follow the Data Explorer's motto of visualize, visualize, visualize. So let's create another section. I'm going to write here a title called Create a Function to Display Random Images. And sure, we've had a look at the different attributes of our custom dataset. We see that it gives back a list of different class names. We see that the lengths are similar to the original, but there's nothing quite like visualizing some data. So let's go in here. We're going to write a function, a helper function. So step number 1, we need to take in a data set. So one of the data sets that we just created, whether it be train data custom or train data, and a number of other parameters, such as class names and how many images to visualize. And then step number 2 is to prevent the display getting out of hand. Let's cap the number of images to see at 10, because look, if our data set is going to be thousands of images and we want to put in a number of images to look at, let's just make sure it's the maximum is 10. That should be enough. So we'll set the random seed for reproducibility. Number 4 is let's get a list of random samples. So we want random sample indexes. I'll just get rid of this S. From, what do we want it from? From the target data set. So we want to take in a data set, and we want to cap the number of images we're seeing. We want to set a random seed. And do you see how much I use randomness here to really get an understanding of our data? I really, really, really love harnessing the power of randomness. So we want to get a random sample of indexes from all of our data set. And then we're going to set up a matplotlib plot. Then we want to loop through the random sample images and plot them with matplotlib. And then as a side to this one, step 7 is we need to make sure the dimensions of our images line up with matplotlib. So matplotlib needs height, width, color channels. All right, let's take it on, hey? So number 1 is create a function to take in a data set. So we're going to call this def, let's call it def display random images, going to be one of our helper functions. We've created a few type of functions like this, but let's take in a data set which is torch utils of type, that is, of type data set. Then we're going to take in classes, which is going to be a list of different strings. So this is going to be our class names for whichever data set we're using. I'm going to set this equal to none. And then we're going to take in n, which is the number of images we'd like to plot. And I'm going to set this to 10 by default, so we can see 10 images at a time, 10 random images that is. Do we want to display the shape? Let's set that equal to true so that we can display what the shape of the image is, because we're passing it through our transform as it goes into a data set. So we want to see what the shape of our images are just to make sure that that's okay. And we can also, let's set up a seed, which is going to be an integer, and we'll set that to none to begin with as well. Okay, so step number 2, what do we have above? We have, to prevent the display getting out of hand, let's cap the number of images to see at 10. So we've got n, is by default, it's going to be 10, but let's just make sure that it stays there. Adjust display if n is too high. So if n is greater than 10, let's just readjust this. Let's set n equal to 10 and display shape. We'll turn off the display shape because if we have 10 images, our display may get out of hand. So just print out here. For display purposes, n shouldn't be larger than 10, setting to 10 and removing shape display. Now I only know this because I've had experience cooking this dish before. In other words, I've written this type of code before. So you can customize, the beautiful thing about Python and PyTorch is you can customize these display functions in any way you see fit. So step number 3, what are we doing? Set the random seed for reproducibility. Okay, set the seed. So if seed, let's set random.seed equal to that seed value, and then we can keep going. So number 4 is let's get some random sample indexes. So we can do that by going get random sample indexes, which is step number 4 here. So we've got a target data set that we want to inspect, and we want to get some random samples from that. So let's create a random samples IDX list, and I'm going to randomly sample from a length of our data set, or sorry, a range of the length of our data set. And I'll show you what this means in a second. And the K, oh, excuse me, have we got enough brackets there? I always get confused with the brackets. The K is going to be N. So in this case, I want to randomly sample 10 images from the length of our data set, or 10 indexes. So let's just have a look at what this looks like. We'll put in here our train data custom here. So this is going to take a range of the length of our train data custom, which is what? 225. We looked at that before, just up here. Length of this. So between 0 and 255, we're going to get 10 indexes if we've done this correctly. Beautiful. So there's 10 random samples from our train data custom, or 10 random indexes, that is. So we're up to step number 5, which was loop through the random sample images or indexes. Let's create this to indexes, and plot them with matplotlib. So this is going to give us a list here. So let's go loop through random indexes and plot them with matplotlib. Beautiful. So for I targ sample in enumerate, let's enumerate through the random samples IDX list, and then we're going to go targ image and targ label, because all of the samples in our target data set are in the form of tuples. So we're going to get the target image and the target label, which is going to be dataset targ sample. We'll take the index, so it might be one of these values here. We'll index on that, and the 0th index will be the image, and then we'll go on the data set as well. We'll take the targ sample index, and then the index number 1 will be the label of our target sample. And then number 7, oh, excuse me, we've missed a step. That should be number 6. Did you catch that? Number 5 is setup plot. So we can do this quite easily by going plot figure. This is so that each time we iterate through another sample, we're going to have quite a big figure here. So we set up the plot outside the loop so that we can add a plot to this original plot here. And now this is number 7, where we make sure the dimensions of our images line up with matplotlib. So if we recall, by default, PyTorch is going to turn our image dimensions into what? Color channels first. However, matplotlib prefers color channels last. So let's go adjust tensor dimensions for plotting. So let's go targ image. Let's call this targ image adjust equals targ image dot permute. And we're going to alter the order of the indexes. So this is going to go from color channels, or the dimensions that is, height, width, and we're going to change this width, if I could spell, to height, width, color channels. Beautiful. That one will probably catch you off guard a fair few times, but we've seen it a couple of times now, so I'm going to keep going with this. Plot adjusted samples. So now we can add a subplot to our matplotlib plot, and we want one row of n images. This will make a lot more sense once we visualize it. And then for the index, we're going to keep track of I plus 1. So let's keep going. So then we're going to go plot im show, and I'm going to go targ image adjust. So I'm going to plot this image here. And then let's turn off the axis. And we can go if the classes variable exists, which is up here, a list of classes. Let's adjust the title of the plot to be the particular index in the class list. So title equals f class, and then we're going to put in here classes, and we're going to index on that with the targ label index, which is going to come from here, because that's going to be a numerical format. And then if display shape, let's set the title equal to title plus f. We're going to go new line shape. This is going to be the shape of the image. Targ image adjust dot shape. And then we'll set the title to plt dot title. So you see how if we have display shape, we're just adjusting the title variable that we created here, and then we're putting the title onto the plot. So let's see how this goes. That is quite a beautiful function. let's pass in one of our data sets and see what it looks like. Let's plot some random images. So which one should we start with first? So let's display random images from the image folder created dataset. So this is the inbuilt PyTorch image folder. Let's go display random images, the function we just created above. We're going to pass in the train data, and then we can pass in the number of images. Let's have a look at 5. And the classes is going to be the class names, which is just a list of our different class names. And then we can set the seed. We want it to be random, so we'll just set the seed to equal none. Ooh, doesn't that look good? So this is from our original train data made with image folder. So option number 1 up here. Option 1, there we go. And we passed in the class name. So this is sushi, resized to 64, 64.3. Same with all of the others, but from different classes. Let's set the seed to 42, see what happens. I get these images. We got a sushi, we got a pizza, we got pizza, sushi, pizza. And then if we try a different one, we just go none. We get random images again. Wonderful. Now let's write the same code, but this time using our train data custom dataset. So display random images from the image folder custom dataset. So this is the one that we created. Display random images. I'm going to pass in train data custom, our own data set. Oh, this is exciting. Let's set n equal to 10 and just see how far we can go with our plot. Or maybe we set it to 20 and just see if our code for adjusting the plot makes sense. Class names and seed equals, I'm going to put in 42 this time. There we go. For display purposes, n shouldn't be larger than 10, setting to 10 and removing shape display. So we have a steak image, a pizza image, pizza, steak, pizza, 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 steak, pizza. If we turn off the random seed, we should get another 10 random images here. Beautiful. Look at that. Steak, steak, sushi, pizza, steak, sushi, class. I'm reading out the different things here. Pizza, 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 pizza. Okay. So it looks like our custom data set is working from both a qualitative standpoint, looking at the different images, and a quantitative. How about we change it to 5 and see what it looks like? Do we have a different shape? Yes, we do. The same shape as above. Wonderful. Okay, so we've got train data custom, and we've got train data which is made from image folder, but the premises remain. We've built up a lot of different ideas and we're looking at things from different points of view. We are getting our data from the folder structure here into tensor format. So there's still one more step that we have to do, and that's go from dataset to data loader. So in the next video, let's see how we can turn our custom loaded images, train data custom, and test data custom into data loaders. So you might want to go ahead and give that a try yourself. We've done it before up here. Turn loaded images into data loaders. We're going to replicate the same thing as we did in here for our option number 2, except this time we'll be using our custom data set. I'll see you in the next video.